everyone, this is chapter 5.3, which is the fundamental theorem of calculus, and this is where we start to finally see that link between antiderivatives and the definite integral. So it's pretty nice, but let's take a look. So there's actually two parts to the fundamental theorem of calculus, otherwise known as FTC for short. Actually, the second part's more useful in my opinion, and we'll kind of see that as we go along. But we'll at least have to see the first part in order to have an understanding of what's really going on, and then it'll make the second part, which is more useful, more, well, I guess easier to understand. So at least that's the goal. So let's see. So the first part of the fundamental theorem of calculus says, if f is a continuous function on the closed interval a to b, then the function g, defined by g of x equals the integral from a to x of f of t dt, where x is in between a and b inclusive, then this function must be continuous on the closed interval a to b, differentiable on a to b, open interval a to b, and the derivative of g is f. Now, something to kind of understand, have the understanding of, is what g is doing. So g is actually looking at the integral from a to x of, well, f. So this is the function f, and the area in between a and x is going to be g. So the area here represents g of x. So notice x can actually move. A, it actually doesn't really matter what a is. A is just some value that's less than x, basically. So, right. And then x is going to be obviously smaller than b, so x is in between a and b somewhat. Great. So now, how we can prove this, honestly, the proof isn't that big of a deal, but I want to give you some type of idea as far as what's going on here. So the way I'm going to prove this is by the definition of derivative. So I'm going to say first here that g prime of x is equal to, if we recall the definition of derivative, limit as h goes to 0 of, well, that's going to be g of x plus h minus g of x all over h. And of course, we can take derivative because g is continuous, and if it's differentiable, that means this limit exists, and we're going to find that out right now. And furthermore, we'll show that the derivative is f of x. At least we'll kind of show it. I won't really talk about too many details, but we'll get a really good idea as far as what's going on. So notice g of x plus h and g of x. G of x plus h is the integral from a to x plus h of f of t dt, minus the integral from a to x of f of t dt. Now you'll notice here that we're not using x's in the integral, we're using t. So this t is what is known as a dummy variable because, well, basically the integral will represent the area under the curve, but it's going to be in terms of x actually. So the t doesn't actually really matter as it turns out. And it kind of makes sense because if you look at the integral of a function of x dx, you end up getting a number that represents the area. But here the area will be dependent on where we're going to from a. So it's going to be in terms of x, not in terms of this variable t. That's why we call it a dummy variable. And this is, of course, all over h. And we're still in the limit as h goes to 0, of course, so I'll include that, of course. And now, we're going to use some properties here of the integral. We can split this integral up as the integral from a to x of f of t dt, plus the integral from x to h, or I guess x to x plus h, really I should say, of f of t dt, minus the integral of a to x, that's a second term there that we're subtracting in the numerator, of f of t dt. And what you'll notice is we definitely have some cancellation here. The integral from a to x is cancel out, so we're only left with this, and moreover it's all over h, which I'll just denote as multiplying by 1 over h on the outside like this, and then again we're still in the limit as h goes to 0. So really we have a limit as h goes to 0 of 1 over h times the integral from x to x plus h of f of t dt. So really what we want to show here is this limit is actually equal to f of x, and it's not too difficult to do using the extreme value theorem along with the squeeze theorem actually. So I need a little bit of space. I'm going to erase this, lift this up over here, and then continue the proof. Right, so I've shifted this up, and this is the result we just had. G prime of x is equal to this limit. Now the next part is a little strange, but it's not too bad. I'll write it over here. Basically, the extreme value theorem implies that on the closed interval from x to x plus h, f achieves a maximum, capital M, and a minimum, absolute minimum, lowercase m. So we can say that there exists m and capital M such that f of t is in between those. Okay. Furthermore, we can say that these are values on the function, so they're f of something. So in fact, we can definitely do that. But the first thing I'm going to do is I'm going to integrate everything with respect to x and x plus h. And you'll see why in a second. So if you take the integral from both sides with respect to, so this is true for any value of t in between x and x plus h. But if we integrate both sides, or I guess all three sides of this, with respect to t, we end up getting this, which by the way we can do from comparison properties that we saw from the integral from the last section, which I said don't come up too often, but this is one area where it does come up. We're taking the integral from x to x plus h, and what you'll notice is that since we are integrating constants on the end parts of this inequality here, from what we saw from the integral of a constant, it's just that constant multiplied by the difference of the bounds. Now x plus h minus x, the x's cancel, so we literally just get m times h. Similarly here, on the other side, we get capital M times h as well. And then again, that's just because the integral of a constant is a constant times the difference of the limits. Basically because it's going to be a rectangular area. But again, we saw that in 5.2. So now if we divide through by h, we'll get that this is legitimately in between m and lowercase m and capital M. So in fact, we can say that this is actually in between. So 1 over h times the integral of f of t dt from x to x plus h is legitimately in between capital M and lowercase m. Just dividing through by h, we get this. So let me just say divide through by h, we get that. And the fact that these are points on the function, again by extreme value theorem. So in other words, there exists a value v such that f of v is capital M, and a value u such that lowercase m is f of u. And then the next thing we're going to do is we're going to take the limit as h goes to 0. So as h goes to 0, u and v will both approach x. And the reason there is because m and m will actually be the maximum and the minimum in that closed interval. So it's really best to visualize it like this. We have x and x plus h over here. We have some function, let's say f, and let's just say that here's the max. So the height here is m, capital M. Yeah, I guess that works. And here we have this minimum, and it's lowercase m. But notice what happens. As h goes to 0, these become the same. Because h goes to 0, you have x and x, so they kind of close in. Meaning these 2 points will approach the same one f of x value. So as h goes to 0, these each approach f of x. So then we can say by the squeeze theorem, since this integral is in between f of x, it must be equal to f of x. So now I'm going to clean up the board a little bit and write that, and that'll be actually the end of the proof. Let me just kind of finish up this last thought here. There we go. So by the squeeze theorem, this must be equal to f of x. So I'm going to write that here, and that'll complete the theorem. All right, so by the squeeze theorem and a bunch of other funny things, we ended up getting that this integral is actually equal to f of x. That completes the proof. We showed that g prime of x is equal to f of x. In other words, its limit exists, meaning that it's differentiable. The function g of x, as it's defined here, is differentiable in the open interval a to b. The one thing I must say is the way I kind of define this proof is if, well, h was positive. If h was negative, well, the inequality we worked out would kind of be true in a different way, but actually the same logic still applies. Why we would need h to be negative is because notice this limit is not a one-sided limit, it's a two-sided limit. So h could approach 0 from the positive right side or the negative left side. So I hope that makes sense. Now let's see some examples of this finally, and then we can move on to the second part. Alright, so these are actually the only two examples I'm going to be doing on the first part of the fundamental theorem of calculus. Honestly, I think this is really all we need to see, and from this you can get a good idea of how to do problems that are similar to ones like these. Now here we're being asked to find the derivatives of these functions g of x. They're defined as integrals where our lower limit is a constant and the upper limit is something in terms of x. So let's see if we can proceed. So notice here, this is our f of t. So by the fundamental theorem, by FTC part 1, let's call this FTC 1, then we get that g prime of x is equal to, well, f of x. Perfect. So what's f of x? F of x is the inside, the integrand, radical 1 plus t squared, but only instead of t we're using x. Because it's not f of t, now it's f of x when you take its derivative. Awesome. So that's really it for the first example here. The second one's a little harder because our upper limit isn't just x, it's x to the fourth. So there's something actually you have to do that's a little different, and it's a little harder to see why that's the case, but really I'll just tell you right now, this is a chain rule problem. And the reason being is because we expect this function to be x, but instead it's another function of x. So here we have literally a composition of functions. We have a function of a function. So g of x is some function of x to the fourth. Basically, you can think of it like that. So in other words, by the fundamental theorem part 1, so FTC 1, g prime of x is equal to the derivative of this, again by the fundamental theorem, is, well, this is f of t. So it's going to be f of this upper limit here. So it's going to be f of x to the fourth. But by chain rule, we have to multiply by derivative of that inside function, because here the upper limit is our argument basically for these kinds of weird integral functions. So this is going to be times the derivative of x to the fourth, which is 4x to the third, and that part's by chain rule. Now, what is f of x to the fourth? Well, f of t is secant of t, so f of x to the fourth is secant of x to the fourth. And that 4x cubed I'll just write in front. And this is our answer here for the derivative of g. So that's really, honestly, the hardest to get to these kinds of problems. Literally, if it's just x on top, its derivative is the inside with x instead of t's, or whatever your dummy variable is, but here I've been using t's. And when it's not x, but it's another function of x, you do that, you write it with that function instead of t, but then by chain rule, you have to multiply by derivative of that function. That's the upper limit. Now we're going to take a look at the second part of the fundamental theorem. All right, so here it is in all its glory, the second part of the fundamental theorem of calculus. If f is a continuous function on the closed interval a to b, then the integral from a to b of f of x dx is capital F of b minus capital F of a, where capital F is an antiderivative of f. In other words, capital F prime is equal to lowercase f. Now, it may not seem all that great looking at face value, but this is something people take really seriously. In fact, people actually get tattoos of this statement, believe it or not. I'm not kidding. Here, I'll show you. I'm just kidding. I don't know. But anyways, I'm going to try to prove this here, and I'll prove it using the first part of the fundamental theorem of calculus. So what we're going to do is we're going to say that this integral here is, well, let's do this. Let's say that, obviously, if we call this g of b, then we consider g of a. Notice g of a is just the integral from a to a of f of x dx. We've actually seen an integral property where if the limits are the same, then this integral is obviously 0 because there's no area. So this is legitimately 0. Also notice that since we have from the first part of the fundamental theorem, g prime of b is going to be equal to f evaluated at b. Similarly here, g prime of a, I guess this part isn't as important because it's going to be 0. So since g of a is 0, g prime of a is going to be 0. So that part I don't think is as important. But let's kind of see. So if this is the case, and this means that g is an antiderivative of f, so we can say that g of x is equal to, so from this line up here, g of x is equal to capital F of x plus some constant c. So basically, lowercase g of x and capital F of x are not the same function necessarily, but they share the same derivative so that they're just a constant away from each other, which is an idea we've seen before. And it makes sense because when you take derivative of this, you get g prime of x. When you take derivative of this, you get capital F prime, which we know is just lowercase f from the statement here. And c, of course, goes to 0, so they're both equal in this case. And here b is kind of arbitrary. In fact, really, if I wrote this as being x, then I guess this would have to be some other variable t. Then this statement makes a whole lot more sense. But now in particular, when g is equal to b, though, then we actually have that g of b is equal to capital F of b plus c. Similarly, if we plug in a, we'll also get that lowercase g of a is equal to capital F of a plus some constant c. And if we actually find out what capital F of b minus capital F of a is, here's what's going to happen. We're going to get, well, g of b minus c minus g of a minus c. And notice what happens here is after distributing, we get a positive c and the c's actually cancel out. So we really just end up getting g of b minus g of a. And notice g of a is 0 from the above calculation. And g of b, I kind of wrote it earlier, it's just the integral from a to b of f of t dt. But since t is a dummy variable, we can replace it with x instead of t. And there you go. So we've proven that this right here, looking at the extreme left, is equal to this extreme right part, and that proves the theorem. Awesome. So now this is actually, again, it doesn't look useful just because, doesn't really mean a lot just looking at it for the first time. You have to see an example to really appreciate what's going on. Because remember from what we saw from 5.1 and 5.2, integrals are really hard to figure out because we basically have to find the area under the curve where the curve may be this wavy kind of thing in general. And that's honestly hard to do. But if we have an equation for the function and we can find its antiderivative according to this, it should be super simple. So now let's take a look at a few examples. All right, so here I have 4 examples, and at first, based on what we saw in 5.1 and 5.2, you may think I'm crazy because each integral wasn't a one-liner, it took a little bit of time. But using the second part of the fundamental theorem of calculus, these problems are kind of one-liners. Of course, assuming we can actually find the antiderivative of the integrand. So remember, the integrand here is 3x minus 2, here it's x squared, here it's x squared minus 3x plus 1, and here it's sine of t. Now, the d something, in this case dx, 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 and here dt, should be the same as this variable of our function because that's the one we're antideriving with respect to. So keep that in mind, but that should always normally be the case. Now, the first 3 we actually saw in 5.2 and I think 5.1 as well. This one we saw in 5.2 and I believe these 2 we saw in 5.1. And it took time, but now I'm going to stop hyping it up and let's kind of get right to it. So here, all we need to do, according to the fundamental theorem part 2, is take the antiderivative of this function, which we know is the power is 1. So if you add 1 to the power, you get x squared. Divide by 2, which is the new power, you get this. Minus antiderivative of 2 is 2x. And then we're going to evaluate this between x equals 1 and x equals 5. Now, this notation I didn't actually mention before, and I kind of should have. But basically, this just means we're going to plug in the top one to this, minus plugging in the bottom one into this. Really, this is our capital F of x, this is our b, this is our a. So by the fundamental theorem, we need capital F of b minus capital F of a. So we need to plug in 5. So I'll do that here. So there we go, that's me plugging in 5 minus plugging in 1. So when you plug in 1, you get 3 halves 1 squared minus 2 times 1, and a little bit far off, but yeah, I guess we see it, squeezed it in there. And now, so not quite a one-liner, we're pretty close. Now if we evaluate this, notice we get 25 times 3 is going to be 75 over 2. 75 over 2. There we go, minus 10. Minus, the second evaluation is just literally 3 over 2 minus 2. And then if you distribute that negative, you end up getting 75 minus 3 over 2 minus 10 plus 2. And notice that's just negative 8. This right here, 75 minus 3 is 72. 72 over 2 is, well, that's going to be, let's see, 36. So we get 36 minus 8 and that's indeed 28, which is the answer we got for that one in 5.1. Awesome. So obviously it wasn't super straightforward, but at least it's just literally finding the antiderivative, evaluating, subtracting, and that's it. Here, this will be a lot quicker. Antiderivative of x squared is 1/3 x cubed. Evaluate this between 0 and 1. So we get 1/3 1 to the 3 minus 1/3 0 to the 3. That's 0, so we don't need to worry about that. And this is just 1/3 times 1. So the answer here is 1/3. And that took us a lot of effort to show that this was indeed 1/3. In 5.1, we used that weird summation result of it was summing over square integers, which is a nice result, but look how lovely and quick that was, right? Here, we're going to take the antiderivative, of course, of the inside, the integrand, and that's going to be 1/3 x to the 3rd minus 3 over 2x squared plus x, evaluate between 0 and 3. I'm going to show you that in this case, this doesn't always happen, but in this case, when you plug in 0, the bottom limit, they're all powers of x, so plugging in 0 will just make it 0. So I'm going to cross it out because it'll just be minus 0, kind of like we had up here. But now plugging in 3, notice here we just get 1/3, 3 to the 3rd, which is 27. So I'm going to be a little quicker about this evaluation. Minus 3/2, 3 squared, which is 9, plus 3. So that's just me plugging 3 into this and being a little quick about the evaluation. Notice 3 goes into 27 9 times. 3 times 9 is 27, so this is 9 minus 27 over 2 plus 3. Notice 9 plus 3 combined to 12, so let me write our result over here. We have 12 minus 27 over 2. 12 is literally just, so that's over there. Or I guess we can swing it this way if you like, maybe that's better. So 12, notice, is 24 over 2, so this is 24 minus 27 all over 2, which is negative 3/2. Awesome. Now this one we haven't seen before, and honestly I don't think we were really able to do this by any non-calculus means. This one I think is the first example of a result that we can only do using the fundamental theorem. So here we're going to get the following. Antiderivative of sine of t is negative cosine of t. Okay. Evaluate between the limits 0 and pi. Now notice above I plugged in 0 and we got 0. Here, not the case. And I even said that doesn't always happen. And this is a good example of that. It doesn't happen here because cosine of 0 is not 0, it's 1. So now plugging things in, we get negative cosine of pi, like that for the first evaluation, minus negative cosine of 0 for the second evaluation. Now cosine of pi is negative 1, so this is negative 1, which is positive 1. So let me write that here. This is negative 1, so we get a double negative, so that just gives us positive 1 for the first evaluation. Cosine of 0 is 1, so this is also double negative 1, so that gives us 1 for the second evaluation. 1 plus 1 is 2, so the result here is 2. Now I want to show visually what this represents because it's kind of nice. Basically, if you look at the graph of sine, it's this kind of sine wave looking thing. This is one period. If you were to draw more periods of sine, you can kind of get this wave that extends indefinitely across the x-axis from negative infinity to infinity. What we have found is the area under the curve between 0 and pi. So we have found out that this area, the area of this hump here, is just 2, which is kind of surprising because it looks circular, at least the way I drew it. So you'd imagine that it would have something to do with pi, but surprisingly it's just an integer. The area, that is just an integer, which is quite striking to me. So yeah, I don't know if we should do more examples. I'm just going to do some more examples anyways. So this I think is really fun, and obviously kind of get used to evaluating these sorts of things this way, of course. So now we're going to take a look at a few more examples, and that'll be really the end for this this video. Okay, so these are the last examples we're going to do. I chose them because they're not as straightforward, but really it's just taking knowledge of what we saw in 4.9 for antiderivatives, and recall that while we have a product, and a quotient, we don't have rules for those types of things for antiderivatives, at least not yet. But what we can do though is we can actually split these up into terms somehow. Here we'll distribute, here we'll FOIL, here we'll legitimately split it up, and then write them as powers and use the power rule. So here, there's no sign or e or anything funny like that. Literally, we're just using power rule, but I just again want to remind us that you can't break this up multiplication-wise. We cannot say that this is the integral of the first one times the integral of the second. It is not that straightforward. We instead have to find the antiderivative by distributing, in this case, writing this as a 1/2 power, and let's see what we get. So we get 4t to the 1/2 minus t to the 3/2 inside the integral still. When we take the antiderivative, that's going to be t to the 3/2 divided by 3/2 and multiplied by 2/3. 2/3 times 4 is 8/3. Minus the antiderivative of t to the 3/2 is t to the 5/2. Remember how you add 1 to a power, you can add top and bottom. You get 5 in this case over the same denominator, so 5/2. Divide by that new value or new power, which is multiplying by the reciprocal, 2/5. And then evaluate this expression finally between our limits, 0 and 4. Notice when you plug in 0, it's 0 because our power is of a variable. When you plug in 4, you get 8/3, 4 to the 3/2, minus 2/5, 4 to the 5/2. Now to take something to the 1/2 power is to square root it. So really when we're taking 4 to the 1/2 power, we're looking at the square root of 4, which is just 2. So really this is just 2 to the 3rd and then 2 to the 5th, respectively. Like that. So this is 2 to the 3rd, which is 8. So that's 8 times 8/3. And then 2/5 times 2 to the 5th, which is 32. So then multiplying and combining these, we get 64/3 minus 64/5. Yeah, I'm going to be a little clever here. It's not super clever, but I'm just going to take advantage of some arithmetic by factoring out 64. So this is really 64 times the quantity, 1/3 minus 1/5. That'll make the evaluation a little easier to handle. So notice if we use this kind of crisscross method of subtracting, we get 5 times 1 minus 3 times 1 all over 5 times 3. So namely that's 5 minus 3 over 15, which is 2 over 15 times 64. So this is literally just 128 over 15. Awesome. So that wasn't too bad. Again, it's just anti-deriving and then, well, evaluating and subtracting. So at some point we're just kind of spending time cleaning up the arithmetic. Here we have to FOIL this first. So let's do that. So we end up getting 3 squared, or 3u squared I should say, there we go, plus 3u minus 2u minus 2. Now these two combine to just u, so I'll write that, if you don't mind, as just plus u and then minus 2. This is still in the integral from -1 to 2. We have our first instance of a negative limit, but that won't really mean too much. So we're literally just going to apply the same thing, just kind of keep in mind that we'll have a negative value that we're plugging in. So now the antiderivative of these is not too terrible. Antiderivative of 3u to the second is 3u to the 3rd over 3, or namely just u cubed. And notice you can see derivative of u cubed is indeed 3u squared, so that's fine. Antiderivative of u is 1/2 u to the second. Let me kind of border this off from the previous problem. Okay, antiderivative of 2 is 2u. Now remember, we're using the variable u here, much like we're using the variable t here, much like we're using the variable x here. So kind of stay within those worlds of those variables. But now we need to evaluate this between, I kind of ran out of space. It's a shame. Well, we're going to evaluate this between the values -2 and -1 and 2. That looks okay, I think. So plug in 2. I'm going to be, again, a little quick about this. 2 to the 3rd is 8, plus 1/2 2 squared. 2 squared is 4, 1/2 of 4 is 2. Minus 2 times 2 is 4. So this is 8 plus 2, which is 10 minus 4. So that's going to be 6 for the first evaluation. Minus, for the second evaluation, when you plug in -1, an odd power of -1 is negative, an even power of -1 is positive. So this is -2 times -1, which is positive 2. Notice that these combine to positive 1. So this is 1 1/2 or 3/2. So that's -3/2. Now, of course, 6 is 12/2. So 12 minus 3 is 9/2 then. Or you can also see this as 6 minus 1.5 is 4.5, which is a fraction is 9/2. So that's not too terrible. Awesome. Now with this one, we have to split this up So I'm going to actually write this as a 1/2 power at first. Then I'm going to split this up like this, 1 over x to the 1/2 plus x squared over x to the 1/2. Then we're going to subtract the power, so I hope you don't mind that I simplify it like this as we go along, or at least by erasing and rewriting. So this is going to be the integral from 1 to 4 of x to the negative 1/2 plus x to the 2 minus 1/2, which is x to the 3/2. Because 2 minus 1/2 again is 1/2, which is 3/2. So now we need to find the antiderivative of these, then evaluate. So we're going to add 1 to the power to get 1/2, multiply by the reciprocal 2, add to the power, add 1 to the power, so we get 5/2, multiply by the reciprocal 2/5, then evaluate between 1 and 4, just like that. Plug in 4, remember that when we're taking it to the half power, we're square rooting. So 4 to the 1/2 is 2, times 2 is 4, plus 2/5 times, let's see. So remember, 4 to the 1/2 is 2, and then 2 to the 5th is 32. In fact, we did 4 to the 5/2 above, so that's not too surprising, I think. So this is our first evaluation here. Minus for our second evaluation, we're plugging in 1. So 1 to any power is just 1, so we literally just get the coefficients, 2 plus 2/5. So that's 2 plus 2/5. By the way, this, notice if you multiply straight across top and bottom, you get 64 over 5. So I'm going to write it like that. 64 over 5. And if you actually, distribute this and subtract, 4 minus 2 for the integers is going to be 2, plus for the fractions that are over 5, we get 64 minus 2 over 5, which is 62 over 5. And of course, 2 is the same as 10 over 5. So this all comes together as 72 over 5. And awesome. That's it there. So nice. Whew. Really cool. So again, 5.3 simplifies things a lot. In fact, this connection really allows us to find antiderivatives, or I guess integrals, which represent areas under the curve, just using antiderivatives. So I didn't actually graph these integrands and show what the function looks like. It would be useful to do that within these x values here, I guess t and u and x values, so we can see what the area looks like, because these values represent the area of those regions. Now remember that you can get a negative the way it's defined, because if it dips below the x-axis, then it represents a negative area. So just keep that in mind, that can possibly happen. You can also get 0, for instance. In fact, when we looked at sine from one of the previous examples, if we actually took the integral from 0 to 2 pi, since this is 2 and this is negative 2, that would have to be 0. So that's just an example of that. And that's really all I want to say for 5.3. So it was not really too much, but at least it was pretty fun. I'd like to say, hopefully you agree and had fun as well. I think this is a really nice section because it kind of shows a lot of technique, and it allows us to kind of use, I guess you can kind of say, shortcuts. In fact, one might kind of see this as equivalent to the beginning of chapter 3, where we saw a lot of shortcuts in finding derivatives. And it's a really good analogy, actually, because if you think about it, we learned derivatives the long way by definition, finding equations of the tangent line, seeing that relationship, and then finally the shortcuts just made it super simple to take the derivative. And here we're kind of doing the same thing in reverse, only it really represents a value. Now in the next section, 5.4, we're going to be discussing the indefinite integral, which literally is just the antiderivative. There's not really too much to say there, honestly. Essentially we have no limits, and the integral of a function is just its antiderivative. That's what we define the indefinite integral to be. We'll take a look at that when we get there, and then 5.5 will also, that's gonna be crazy. Because in 5.5, we'll learn to take the integral of things that at face value seem we can't, but then using a little trick, we'll be able to. And that'll be the end of chapter 5. So that's gonna be a lot of fun. I'll see you in the videos for that. Thanks for watching this. Hope you enjoyed, and I'll see you then.